Tak, będę musiał sprawdzać co chwileczkę, bo czasem też ten smartfon przestaje działać. And so we are shifting into English, and of course, if you will have any problems with understanding of something like that, the quality by Teams, also the quality of voice transmission is not sufficient, I would say. So the quality on smartphone would be much better. And first, what I would like to start with is some information on the conventions that we are using in organic chemistry. So organic chemists are accustomed to, arrows or some kind of method of writing reactions, of noting the structure of the molecules, formula of these molecules that we are reacting in the reactions, but it is not as obvious as we would expect. So first, let's say such a term as chemical compound. What does chemical compound means? Yeah, everybody would say chemical compound is chemical compound. However, basically we have two representations. First are molecules of the matter, two representations of the matter, I would say. So first are molecules and the second are substances. What does chemical compound means? Are chemical compounds substances or molecules? If I ask such a question, would anybody would like to answer that and join the discussion? Or should I proceed now? Okay, the answer is that is not clear. And if we go to the definitions by UPAC, we'll not find any definition of chemical compound. And the whole chemistry is about chemical compounds. So basically, what we mean when we are using a term chemical compound is either it is a molecule or it is a substance. So what the real meaning is, it depends upon the context. So between chemists, we must understand that. And I can say even such a joke that the guys who are working, for example, in chemoinformatics, in pharma companies, they always should be chemists. So it is one of the reasons that there are many terms which could be understood only by chemists. For example, a guy from computer sciences, he cannot understand that easily. So the guys in pharma industry, they always picking the chemistry students to work in that area and not computer science. So basically we have several cases here. So we can have a molecule, let's say in a virtual reality, for example, a molecule within the computer, which is of course a kind of a model of chemical compound, a single molecule. We also can have a single molecule under measurement. Measurement is a term measurement is a term which is defined in UPAC nomenclature, and you can check for that. You can just go into the internet where all the terms which UPAC cares to define could be found easily. So we can also have a single molecule in an experiment. For example, in mass spectrometer, theoretically we can observe a single molecule also. Of course, it is very hard to observe such a single molecule. However, if we, for example, take a single DNA molecule, then we can see that even a simple optical microscope. I only see if my smartphone is still working. Yeah, it's still working, no problem. So two cases here, virtual reality and experiment. And a substance, of course, a substance is just a set of molecules which is basically used in lab, so in vitro experiments, for a real experiments, for a real chemical laboratory experiments. So such a simple term, and we can see that we have some problems here. And the next thing which I would like to explain is the complexity of chemistry. And we can just draw such a triangle, and at the very bottom we'll have physics, then chemistry, then we'll have biology, then we'll have medicine, psychology, and here at the very top of that triangle we'll have economy. So it is just what you can find in the literature, the complexity of sciences and humanities, because of course here at the very bottom we have sciences in English. Sciences are hard science, which could be represented by the data, by numbers, which could be modeled. And here at the very top we have very fuzzy humanities more than sciences. So economy, and we have now something like behavioral economy. So basically people are behaving not very rationally in that area. We can see that now, for example, as the vaccines are distributed through the world, and it is not quite sure if we should pay more or less money. No one can predict it. It's not very easy. Similar at the stock, let's say Wall Street, the representation and the prices on the market is also very vague, defined, and it's not easy to be predicted. Otherwise everybody will be a millionaire. So it's not so easy. So why such a triangle or a pyramid? All sciences or humanities are using a science which is on the bottom of that one, and to simplify the methodology it used. For example, in chemistry we used physics for the representation of atoms, and basically this physical representation of atoms provides us the possibility to study or to investigate the matter or the properties of chemical matter or substances and so on. For example, theoretical chemistry provides us the access to simulation of such problems. So biology is more complex than chemistry. For example, biology needs chemical representation to model DNA or RNA. And medicine is even much more complicated, and we need psychology also to explain some problems, some medical problems. And at the very top is economy, because if somebody does not have health insurance, he cannot take any medication. So economy defines our life, and it's very important, very important. So let's say, why such many problems with environmental pollution? It's not a matter of chemistry, it's a matter of economy. There's not enough money. So why we are buying, things from China? Because they are cheap. So that's economy. They are not always the best one. However, they are of course better and better. So this triangle allows us or gives us a possibility for understanding what's going on. Each science, each humanity on the top of other use the methodology below to explain its complexity. Very important thing, to understand that even chemistry is soft science. It's a soft science. For example, physics is hard science. What does mean hard science? It means that we will have all the data very defined very clearly. For example, physicists, they are studying, for example, the movement in the gravitation, gravitation, I could say that easier. So we have large balls, for example, and they put them down from the towers, like let's say in Pisa Tower, and observe the time of free movement to the earth. However, okay, that's not the difference. I mean the size of the objects that the science is investigating. For example, physicists are also studying the particles, the very small particles, but then they have, the representation of a movement of the particles very clearly defined, and they can try to model their movement by mathematical equations. And let's say take now chemistry. In chemistry, say let's take a mole of a substance. And what is a mole of a substance? A mole of a substance is, let's say, an Avogadro number of the molecules. However, how to count an Avogadro number of the molecules? It's completely unrealistic. So we are just weighting the molecules, and of course this could be done only in a very not very precise method. Okay. Then, okay, I'll just put that down. Yeah, telephone, they should wait for a while. So, we are formulating this just saying that chemistry is simply a soft science. And there are many examples like that. If something is defined very precisely, then chemistry are taking that, physicists are taking that from chemistry area, and they are working in that branch of physics or chemistry. Let's say we have crystallography, and we have the crystallography units both in chemical and physical departments. So it is both chemistry and physics. However, then if we analyze what the people are doing there, it is always that physics or physicists have much better defined data than chemists. Do chemists would like to have such data? No. Someone must work in that area. For example, drug design, very unspecified. Let's say the relationship between the structure and the activity of such chemical compounds. We now know what chemical compounds really means. And Then I would like to say something about the convention which we are using in chemistry to support such a complexity to describe each year better and better, of course, that complex chemical world. And at first, let's say, are chemical names, nomenclature, chemical names of chemical compounds. Chemical compounds, so the name relates both to substances and molecules. A molecule has a same name than a substance. And let's say, for example, so nomenclature. And now we can find the nomenclature rules only in the network, in the internet. The books with nomenclature I don't have here. I think the original book with chemical names I don't have here, but usually that were very, very large books printed, and now they are not printed any longer. Let's say such a simple compound like benzene. Yeah, benzene, and test question is it a benzene or cyclohexatriene? So we have 3 double bonds and cyclohexyl structure here. This looks much more regular than the first benzene, and to our surprise it is a right regular name and not that one. Why, the question is? Benzene is just a term which has been taken from gum benzoin, a natural substance which had been obtained in ancient times. I mean, ancient times, not a real ancient, but somewhere in Middle Ages or even before, from the trees. And then that name has been used for the description of such a molecule, and first, of course, such a substance. Of course, it is an aromatic structure, and we very often are asking, let's say, the guys who are going through the doctoral examination, what does mean this aromatic? Aromatic, of course, it relates to a smell of the substance. However, a smell of a substance? Okay, we say no. Aromatic structure here means that we have a certain structure of the double bond and single bond, and a certain regulation, let's say the Hickel rule, which defines such molecules, for example, in benzene. So first the question, why benzene and not cyclohexatriene? Because that is not a cyclohexatriene. Then we say cyclohexatriene, something in the intuition, we are thinking that we have 3 isolated double bonds, and that's not true. That's an aromatic structure. We have something like that. So we have the localized double bond within the whole cyclohexyl ring here. So aromatic refers both to the molecule, because what we are drawing here is a molecule, but if we multiply that, I mean many structures in the substance, we will observe some properties, and these properties are also not typical for all compounds. They are typical for the aromatic structure. So, for example, the substances always tends to preserve that structure which we indicated here, but that delocalized double bond, single double bond superposition or something like that, I could say. Of course, we can say that we can present all of that by the resonance structures and so on and so on. The moment I'll also discuss that, because everything in that area are a matter of the conventions which we are using, and we should be aware of that conventions. Few years ago, let's say maybe 20, the nomenclature was very complicated. So you even cannot feel how complicated the naming of compounds could be, because today we are drawing a molecule on the screen, a computer screen, and immediately we have a name, and we can say that an important contribution to this field of nomenclature in computer in silico, we can say, a nomenclature in silico, is by Janusz Wiśniewski, who is a chemist. He just made his habilitation and professorship in Poland, and then he emigrated to Germany. He's working in Beilstein Institute, and he just wrote the program, Autonom program, which is used for that translation of the molecule structure to the name. So we are just making such a change to have a name which are formed out of the molecular structure. And so today nomenclature is no more so important, but previously we have a very, very large books in which each student should be very good, because otherwise we couldn't have found the molecule we would like to synthesize, for example. Today the computer is working for us. Then the next problem are chemical compounds and reactions. So reactions, basically it is what we'll discuss here during this lecture.